So in this lesson, we're going to introduce you to the factor analysis method or the unit analysis method. This is a general method for solving problems in science where you essentially have an algebra word problem. And we're going to look at this first through the example of doing what's called a unit conversion. So in this particular problem, we're asked to express 6.350 centimeters in a new unit of the inch, right? So if we have 6.350 centimeters as a length, what is that same length in inches? Well, the general procedure in any of these types of problems is first to write down the information that you're given. Where do you start in this problem? We're starting here at 6.350 centimeters. Then ask yourself the question, well, where am I trying to go? What is my final answer? I'm trying to express this in inches. So there's my solution output with the new units. Will be some value. We don't know what it is, but it's going to be in inches. And what we need to find now is a bridge to take us from this value in centimeters to this value in inches. So the relationship happens to be, this relation is that there are 2.54 centimeters in 1 inch. So this is the relation that we need. This value here, what we need to do now, we need to take this relation and convert it to what we call a conversion factor. So if we divide both sides of this equation by 2.54 centimeters, we haven't changed anything, right? In algebra, whatever you do to one side of the equation, if you do the same thing on the other side, you haven't changed anything. When we do this operation, what we end up with is this. We have now 1 inch divided by 2.54 centimeters is equal to 2.54 centimeters divided by 2.54 centimeters. So 2.54 divided by 2.54 cancels to give us 1, and centimeters divided by centimeters gives us no unit at all. We just end up with this relation 1, right? This length divided by the same length equals 1. What's also interesting is that this value divided by this value also is 1 with no units. Now, that may look funny because the numbers are different. But I want you to remember that if you think of the quantity 1 inch, 2.54 centimeters is the same quantity. So the same quantity divided by the same quantity, the same length divided by the same length gives us the relation 1. So this is going to be important when we do the multiplication. Now, if we take this relationship right here, this is called a conversion factor. Okay? And this is the one that we want to use in the problem, because if we start here and we multiply by this conversion factor, again derived from this relationship, look at what happens to the units. We have 6.350 times 1 divided by 2.54 in the numbers, and in the units we have centimeters times inches divided by centimeters. So centimeters divided by centimeters cancels. And now the only unit we have is inches, which is what we need. We put 6.350 into our calculator, divide by 2.54, and we get the value 2.500 inches. Now, a couple of things. First of all, we started by looking at the units. Centimeters, we wanted to find inches. We needed to define a relationship to go from centimeters to inches, which we found. We used this to construct a conversion factor, this relationship, which puts centimeters in the denominator so that these units cancels, and then the unit that we want, that we're trying to solve to, is on top. And in terms of significant figures, the 1 here is exact and 2.54 is exact. In other words, if you have exactly 1 inch, there will be 2.54 centimeters exactly. It's a definition. So The 1 and 2.54 do not enter into our thinking for uncertainty or significant figures. So this is the only thing we have to think about in terms of significant figures. We have 4 significant figures here, so we must have 4 significant figures in our final answer, which is why we have these 2 zeros here. Otherwise, we're throwing away information. Okay? The other important thing is that it's possible to construct a different conversion factor, right? If I divided both sides by 1 inch instead, so I have the same relationship. Now divide by 1 inch. Well, 1 inch divided by 1 inch cancels, and now I have a new relationship, right? This whole thing is also equal to 1. Now, I would use this conversion factor if I wanted to do the opposite. If I had started with inches and I wanted to go to centimeters, then this is the one that I would want to use, so that inches cancels and I get to centimeters. So the point of this system is that focusing on the units allows you to construct a path to solve from a point that you're given to a point that you're trying to get to by constructing conversion factors and canceling units that'll get you to that point. And then finally, we end up with this result. The length, 6.350 centimeters, equals 2.500 inches. This is like multiplying by 1 because the lengths, or the quantities here, are identical, right? Multiplying by 1 does not change the input value of our problem. So again, if we wanted to do the opposite, instead of going from centimeters to inches, we wanted to go to inches to centimeters, you'd start with the same relationship here, and we would write a solution map starting with inches, write down where you're trying to go to, which is centimeters, use this relationship. Now we would look at this conversion factor with centimeters on top, inches on the bottom, so that inches cancels, and we would get centimeters in our final answer. All right, now let's look at a problem. Say your calculator weighs 192 grams and you're asked, what is its weight in pounds? Well, again, solving this using this procedure, you would start with your information that you're given, which is 192 grams. And then you would write, well, what is it I'm trying to solve for? It's some value here, you don't know what it is, in pounds. So LBS is the LBS is the same thing as pounds. LBS is the symbol for pounds. Now, what we need to find is a relationship that's going to go take us from grams to pounds that will allow us to construct the conversion factor. That happens to be this one. And again, you don't need to memorize this, but 1 pound equals 453.6 grams. Generally, in any relationship, the one of something is always exact. And usually this is not exact. So here we have 4 significant figures that we need to keep track of. Now, there's 2 different conversion factors that we can generate from this. If we divide both sides by 453.6 grams, we get this relationship. If we divide both sides by 1 pound, we get this relationship. Which one do we want to use? Well, we're starting with grams and we're trying to get to pounds. So we want pounds on top, grams on the bottom. This is the one we want to use. So let's put it in there. Grams times pounds divided by grams, grams cancels. Okay? So now we're ready to get out our calculator. We put in 192, divide by 453.6, and we'll get this number in our calculator. Now, this value is 3 sig figs. This one is exact, so we don't even enter this into our thinking. If you wanted to, you could think of this as an infinite number of significant figures. And this one is 4 significant figures. So according to our multiplication division rule, we need to report our final answer to which of these has the fewer number of significant figures. So this is 1, 2, 3 significant figures. We need to round this down to 0.423 pounds. And we end up with this relationship. 192 grams is equal to 0.423 pounds. So a word about a number of common equalities. Some of these you already know, like 12 inches in a foot, 3 feet in a yard. These are, by the way, exact. Okay. Some of these you know from cooking, but I will tell you that for the exam purposes, all of these I would actually give to you. Furthermore, all of these I will give to you as well, so you do not need to memorize any of these. However, all of the metric ones, you need to memorize these. In fact, you've already been told you need to do that, because a lot of these are those prefixes. You've got to remember kilo means 10 to the third, or 1,000. 1 times 10 to the third, right, if I substitute K for the number 1,000, I get 1,000 meters, etc. So all of these you need to know. In addition, you need to know that there are 60 minutes in an hour and 60 seconds in a minute. So the method that we've been using all along is called the unit analysis method or dimensional analysis method, mainly because it focuses on the units or the dimensional part of the problem, not on the numbers. So we've been using it for unit conversions so far, but you're going to see other problems in chemistry that are not unit conversions. You're going to use the same system by focusing on the units. Okay? And it's even, since the conversion factors are like multiplying by 1, it's possible to string multiple conversion factors together, as many as you need, to go from the unit that you're starting with to the unit that you're trying to get to. So let's look at a case of that here in a minute. In fact, let's go ahead and just review the systematic approach one more time. We've already been doing this. The first step is to look at the algebra word problem and write down the stuff that's your input, your starting point, the given amounts along with the units. Then write down where you're trying to get to. What are the units of the solution, right? And then you need to construct a solution map. How do you get from your input to your output by stringing together conversion factors? You've got to find equivalent statements for each relationship, then convert each of these equivalent statements to a conversion factor, with the unit that you're starting with needs to be on the bottom of the equivalent statement. Finally, you plug in your numbers in your calculator, and then you need to report the number of significant figures correctly and round to the correct number of significant figures. You also need to verify that all of your units cancels, except for the one that you need to have in your final answer. And finally, don't forget to do this. I failed to mention this earlier. You want to make sure that your answer looks reasonable, right? Is the number magnitude about the right size, and is your unit correct? Okay, so now let's go ahead and look at a multi-step conversion problem. So if you start with 5.89 centimeters, how many nanometers is that? And you're asked to express your final answer in scientific notation. So again, you would start here with your input and write what it is you're trying to solve for, some value in nanometers, and you need to construct conversion factors. Like I said, you can do many of these, as many as you need, to convert from centimeters to nanometers. Now, again, you're not going to be given any of these relations on a test. You need to memorize that there are 100 centimeters in a meter. So there's one relationship that might be useful. Another one is the definition for how many nanometers are in a meter. So there are 1 billion, or 10 to the 9th nanometers in 1 meter. So the Lynch point in this is 1 meter. So if we start with centimeters, I can convert to meters first, constructing one conversion factor. Once I'm in meters, I can convert to nanometers using a second relational factor. So let's go ahead and do this. So we write out 5.89 centimeters. We use this relationship to construct the proper conversion factor. What do we want? We want centimeters on the bottom, so that centimeters cancels, and meters on top. So that's 1 meter divided by 100 centimeters. So if we do that, the centimeters cancels, and now if we put an equal sign, we would have calculated the number of meters in 5.89 centimeters. Since we're trying to get to nanometers, we go ahead and construct another conversion factor. In this case, we want meters on the bottom, nanometers on top, so that our meters divided by meters cancels, and the only unit that we have left, the only one that hasn't been canceled, is the one we're trying to get to. So we've constructed all of this correctly, and again, these factors are derived from equivalent states. So it's like multiplying by 1 in each case. We're not changing the quantity of 5.89 centimeters. We're just going to change the number in the unit, but the length is going to be the same. So you don't even have to get out your calculator to do this, folks, because what we have is 5.89 times 10 to the 9th divided by 100. So using your product rule in the law of exponents, what we have is this: 10 to the 9th divided by 10 to the 2nd power is the same thing as 10 to the 9th times 10 to the minus 2, right? And furthermore, since we have the same base unit 10, all we have to do is add the exponents together. So it's at 9 added to minus 2 gives us 9 minus 2 is 10 to the 7th. So that's our final answer. It's 5.89 times 10 to the 7th nanometers. And we end up with this relationship. 5.89 centimeters multiplied by 1 with no units multiplied by 1 with no units is equal to 58,900,000 nanometers. So these two quantities are identical. Now some of you might be aware enough to also see this relationship. If we have 1 meter, right, 1 meter is our linchpin, and we go up here and we multiply by 10 in each case, that is 10 to the 2nd centimeters, right? 1 meter equals 100 centimeters. If we want to find out where nanometers is on the scale, let's keep going. This would be 10 to the 3rd millimeters. This is 10 to the 4th, 10 to the 5th, 10 to the 6th. This would be micrometers. 10 to the 7th, 10 to the 8th, 10 to the 9th. This would be nanometers. Now, what we want to look at is this is our starting point, this is our ending point. If we look at multiplying by 10, what is the difference? As we go from centimeters to nanometers, this is 10, 10 to the 2nd power, 10 to the 3rd, 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th. So the difference here is a factor of 10 to the 7th. So you could have done this sort of graphically in your head, going straight from centimeters to nanometers. You could write that there in 1 centimeter equals 10 to the 7th nanometers. We sort of derived it from looking at this. I don't recommend that you do it this way unless you've been doing this for a while and you're pretty advanced, okay? But I just thought I'd show this for some of you that might already be thinking about this. You could do it this way if you wanted to. You just have to construct this relationship by looking at the relationships of the units. So what if we have, so we've looked at a problem where you can construct two conversion factors and multiply them together. Here we're going to look at a case where we can use 3. So here you're asked, what is 6.35 ounces expressed in grams? And you're given up front 3 relations. I'll tell you, I'll never give this to you on a test, okay? This relationship, if I put them on a test, will be on the front page. It won't be embedded in the problem. You'll have to know to go to look where these equivalent statements are and pick from them the ones that you need to solve your problem. And of course, this one is one that you're told you need to memorize what kilo means, right? It means 1,000. All right, now where do we start in this problem? Well, we start with what we're given as our input, 6.35 ounces. What are we trying to get to? Grams, some value in grams. So we need to build a solution map to go from ounces to grams. If we look at these 3 relations, the first thing you should do is to look for one that has ounces in it. There's only one that does. It's this one. So we want to start with this relationship. And our conversion factor, we want to construct it with, so we divide both sides by 16 ounces. So that ounces is on the bottom. So the ounces is going to cancel. We will then convert from ounces to pounds. Okay, so that's our first step. Once we're in pounds, we can convert from pounds to kilograms by constructing a second conversion factor. And so this would be step 2. And once we're in kilograms, we can convert from kilograms to grams through this equivalent statement. So here we go. We start with 6.35 ounces. We construct our conversion factor with ounces in the denominator. So we have 1 pounds divided by 16 ounces, so ounces cancels. Then in our second conversion factor, we need to get rid of pounds and convert it to kilograms. So we want pounds in the denominator, kilograms up top. Now our pounds divided by pounds cancels. And then in the third step, we generate a conversion factor from this equivalent statement with kilograms on the denominator and grams up top. So this allows kilograms to be canceled. Now the only unit we have left is the gram, which is what we want. Now we're ready to get out our calculator. We put in 6.35, divide by 16, hit the equal sign, then divide by 2.205, hit the equal sign, and multiply by 1,000, and you'll end up with 179.99 grams. Now, first of all, here we have 3 significant figures. This relationship is exact. In exactly 1 pound, there's exactly 16 ounces, so we don't worry about significant figures in this relationship. In 1 kilogram, there are exactly 1,000 grams. We don't worry about significant figures in this relationship either. This number is exact. This is 1 kilogram. Here we have 4 significant figures. So we have 3 significant figures here. Here we have 4. We're doing multiplication throughout, so this, our product and division rule states that whichever of these 2 has the fewest significant figures is how many we want to round this to. So we want to round this digit here. So we want to round up to 180 with a dot after it. That makes this significant. So we have 3 significant figures, or you could write it as scientific notation. 1.80 times 10 to the second power grams. So that's 0 significant. Now let's look at one more problem. here you're asked to convert 36 cubic inches into cubic centimeters. Now what's different about this problem than the others is that the unit is not of a single dimension. Okay, in fact, this is a cubic inch, and we want to convert to cubic centimeters. So you have to keep track of that. Let's show you what we're talking about here. So we want to convert from cubic inches to cubic centimeters. So we start with this relationship. 1 inch is equal to 2.54 centimeters. We write our solution map starting with 36 cubic inches, and right where we're trying to go to, which is cubic centimeters. So our relationship then, we want cubic inches on the bottom and cubic centimeters up top. Okay? So we divide both sides of our relationship here by 1 inch. But we have to cube the whole thing. So this is important, right? We start here. But to get cubic centimeters and cubic inches, we have to cube the whole thing. And so the cube is operating on the units and the numbers. So what you end up with is 2.54 cubed divided by 1 cubed and centimeters cubed divided by inches cubed, which just equals, right, 16.4 cubic centimeters per cubic inch. So when we solve this problem, we start off with our input, 36 cubic inches. We write what we're trying to get to, some number cubic centimeters. This is the conversion factor we want to use so that cubic inches cancels. And the only unit we have is cubic centimeters. So we get out our calculator, we take 36, multiply by 16.4, keeping track that this is 2 significant figures. This is 3 significant figures. The one is exact, okay? So we need to round our final answer then to 2 significant figures, which is 590 cubic centimeters without the decimal point. Or you could write it in scientific notation as 5.9 times 10 to the second power cubic centimeters. So let's look at one more problem illustrating this unit analysis method that also is using more than one dimension in the unit. So here we're asked to convert 2,659 square centimeters into square meters. The first step is to write down what you're given, which is this value. We know we have 4 significant figures in it. The next thing is to write down what are you trying to solve for, right? Which is some value in square meters. The third step is to find the relationship that's going to go between square centimeters and square meters. So you start with this relationship, that there are 100 centimeters in a meter. And again, I'm not going to give this to you on the test. But we need to know square centimeters to square meters. So we convert this to this relationship, 1 meter divided by 100 centimeters, so that centimeters is on the bottom, and then we square the whole thing. So what we end up with is our input multiplied by our conversion factor. Now this is 100, or 10 to the second power squared is 10 to the fourth. Square centimeters cancels, and now we're ready to get out our calculator. You put in 2,659 and divide by 10,000, or 10 to the fourth power, you get 0.2659 square meters. Now, in terms of significant figures, this is an exact relationship, so none of these values enter into our thinking for significant figures. We have 4 here, so we need to report 4 in our final answer. Both the value and the units are reasonable. So to review this unit, when we think about measurements, we need to think about a number, a unit, and the uncertainty in the measurement. The number can be written either in decimal notation or in scientific notation. The unit may or may not have prefixes which lend further information about the size of the quantity that we're dealing with in the measurement. And finally, how well do we know that if the information in the measurement is by the number of significant figures, right? Where the last digit is our digit of uncertainty. There are also rules that we have to keep track of when we report a final answer in a multi-step calculation for measurements. There are certain arithmetic rules, right? For addition and subtraction, the number of significant figures is irrelevant. It's all about where the uncertainty is in the last relative to the decimal point. And for multiplication and division, the number of significant figures matters. Whichever value has the fewest significant figures, that's the number of significant figures that we need to report in the final answer. And then finally, we've been showing you how to do algebra word problem solving by focusing on the units, right? This is the unit analysis method or dimensional analysis method. You look at some input value of the units, you look at the units that you're trying to get to, you identify a relationship that connects the input unit to the output unit. You construct a conversion factor from it with the starting units in the bottom and the final units on top.